Good evening, or whenever you happen to be watching this. Welcome. I'm Mr. Boothman again, and tonight or today we'll be talking about section 2.3, the real zeros of polynomials. So let's jump right in. Rational zeros of polynomials, we're going to start with first, before we generalize to all real zeros, and then eventually after that we'll rationalize to all zeros of polynomials, real or imaginary. But that's for a little later. For right now, rational zeros. So let's consider this polynomial, p of x equals x minus 2 times x minus 3 times x plus 4. These are all factors. This is in factored form, and we want to write this in standard form. So to do that, we know we need to multiply x minus 2 times x minus 3 times x plus 4. Multiply x minus 2 and x minus 3 together first. In the interest of time, x squared minus 5x plus 6 times x plus 4. And then again, we all know how to multiply, box method or distributing. In the interest of time, I'll go ahead and skip to the answer, x cubed minus x squared minus 14x plus 24. Notice that negative 2 times negative 3 times positive 4 is 24, which is also the constant term here. Positive 24. This is a result of something called the rational zeros theorem. So let's go ahead and talk about that. The rational zeros theorem. If p of x is a polynomial with integer coefficients, then each rational solution p over q satisfies p is an integer factor of the constant term of our p of x, and q is an integer factor of the leading coefficient of our polynomial p of x. So that's a very mathy definition. Let's go ahead and break it apart so we can actually understand it. If p of x is a polynomial, so p of x is a polynomial with integer coefficients, so every coefficient of this polynomial, p of x, is a whole number, positive or negative, then each rational solution p over q, so every solution, every zero of this polynomial that is rational, that can be written as a fraction, p over q, satisfies these two conditions. First, p is an integer factor of the constant term of our polynomial. So in the case above, our constant term was positive 24. So p is any integer factor of that term, whether that's a 3, because 3 times 8 is 24, or that's 24, because 1 times 24 is 24. You get the idea. And q is an integer factor of the leading coefficient of this polynomial. So this polynomial had a leading coefficient of 1, so q is just 1 or negative 1, because we could have negative 1 times negative 1. So let's go ahead and look at another example, start from scratch again, so we can try to make some more sense of this. And at this point, if you're already lost or a little confused, pause, write down questions, take a minute, and then come back to us, and we'll move on. Example 1. Using the rational zero theorem, factor the polynomial p of x equals 2x cubed plus x squared minus 13x plus 6. So our step 1 is to determine all our factors p and q, because our goal is to build up to p over q, since we know that that'll be a rational solution of the polynomial. But we're not there yet, we're getting there. So we have positive 6 And our p is going to be every integer factor of that constant term, positive 6. So what numbers can we multiply to get positive 6? We can multiply positive 1 and 6. We can multiply negative 1 and negative 6 to get positive 6. What else could we do? We could multiply positive 2 and positive 3. We could multiply negative 2 and negative 3 to get positive 6. So those are all of our factors. Next, we need q, and for that we need to look at our leading coefficient. So in this case, our leading coefficient is positive 2. Q is going to be every factor, every integer factor of positive 2. So we could have positive 1 times positive 2 is positive 2. We could have negative 1 and negative 2. So those are all of my p's and q's. Step 2, determine all possible values of zeros. So those are going to be p over q. So now I'm taking each p and I'm putting it over each q. So I could have 1 over 1, positive 1 over positive 1. I could have positive 1 over negative 1. I could have negative 1 over negative 1. So I could have 1 over 2. I could have 2 over 1. 2 over 2. 3 over 1. Plus or minus 3 over plus or minus 2. Plus or minus 6 over plus or minus 1. And plus or minus 6 over plus or minus 2. You can have all of those, but you notice that some of these are the same, right? We have 1 over 1, 2 over 2, 6 over 1. I'm sorry, not 6 over 1, but yeah, 1 over 1 and 2 over 2 are both 1. We have 3 over 1 and 6 over 2. Those are both 3. So we have some multiples here. So if we go ahead and simplify everything, we have plus or minus 1, plus or minus 1/2, plus or minus 2, plus or minus 3, plus or minus 3 over 2, and plus or minus 6. So all of our possible p over q values we just listed. And now we know the rational zeros theorem tells us that in here somewhere are any rational zeros of our polynomial, p of x. How do we check? Well, we know from the factor theorem that if we use synthetic division, if our remainder is 0, then that's a factor. So we want to use synthetic division and start checking. We're just going to start choosing some of these numbers. So I could start with positive 1. I'm going to use synthetic division, so 2, 1, negative 13, and 6. And if my remainder is 0, then I know I have found one of my zeros. One of my factors, one of my zeros. So I'm going to try this here. So 1 is not a 0. Why? Because I ended up with negative 4 as a remainder and not 0. What about negative 1? See, I can already tell. Yep. Negative 1 is not a 0. Let's try 2. I have a good feeling about this one. Yep, so my remainder ends up being 0. That means that 2 is a 0. So we can move on to step 4. Now that we have found a 0 for our polynomial, we also ended up with trinomial here, didn't we? So if 2 is a 0, p of x equals, that means x minus 2 is a factor. And then from here, we have 2x squared plus 5x minus 3. That's our other factor, but that's not factored completely. But now, this is just a quadratic. We know how to factor that. We can use our x. So we can write 2x squared minus x plus 6x minus 3. Factor out an x. And then factor out a positive 3. Factor out 2x minus 1. So this factors to this, which means that our full p of x factored completely is x minus 2 times 2x minus 1 times x plus 3. That's it. So notice that we have 2 is a 0. Negative 3, that means, or x plus 3, that means negative 3 is our 0 here. And then 2x minus 1, it's the same as x minus 1 half. So 1 half is our 0 here. 1 half is there. So the rational zeros theorem, in this case, this polynomial has all rational zeros. That means all of our zeros were in the form p over q, and they were all included in this list here. 1 half, 2, and negative 3. So that could have taken us a really long time. Without our rational zeros theorem, we would have no idea how to find that. It could have been anything, and we could have just kept guessing. In the end, we still had to kind of guess, but at least we could narrow down our list of guesses to this fairly short p over q. And then test using division, synthetic division. So the rational zeros theorem seems like it's kind of long, might be a lot of work, but I promise it does save us a lot of time. So let's go ahead and have you try example 2 on your own, and then we will talk about this in class on Tuesday. So, or I'm sorry, not on Tuesday, we will talk about this on Friday. You won't be watching this until Tuesday. So go ahead, write down questions, bring those to class, rewatch parts of this video if you need to, and make sure that you get the main points, and then we can summarize this and bring it all together, put it all together in class. So for now, thank you, and I hope you have a great rest of your day.